So for this problem, we're going to be using CEA to work on a design problem. So this EconoJet F27W solid motor uses this propellant called white lightning, and it's composed of several different components. So aluminum perchlorate is one of them, hydroxyl turbinate polybutadiene polymer binder, and aluminum powder, and a metal additive. And I know it says and or, but you are expected to include that. And they give you this link right here, which brings you here, so you can see the actual data, so the density of this propellant, the percent of solids, etc. But those two values are the most important right here. So going back to the problem, it gives you this information for aluminum perchlorate, and it gives you two rows with different percentages, and this is the oxidizer. And you can see that they'd have different percentages, so you can choose either or as long as you specify in your assumptions. And so this problem wants you to estimate the propellant formulation with rationale to justify the weight percentage of each ingredient and what is the density of the formulation. So when they say weight percentage, they mean like what percentage of each component is needed in order to make the density equal to what's expected right here. So in order to do that, we need to have an equation, so a formulation. So we have the total density equals the percentage of each component times that component's density. So we have some restrictions on that. So one of the restrictions is that there has to be 82% solid components, and the only liquid in here would be the HTPB, this one. So everything else should be add up to 82%. So yes, that is a constraint that we need. And then that leaves us with 18% liquid, so 18% of this. However, it's not just 18% of HTPB. It's going to be 18% liquid, and this is just one component of it. The other component of the liquid would be, if you go here to this website, not this one, right here, then we go to propellant chemicals. Then we go to this one. Any one of these would work just fine. You need a curative and you need a plasticizer. However, if you choose this one, this curative, it says that you don't need a plasticizer. So 0% is associated with the plasticizer. So we have three components of the liquid. We have the butadiene, the HTPB, the plasticizer, and the curative. So we have 18% of all of that. So 19.4% of 18% would be associated with this chemical. And then 0% for the plasticizer, and the rest of this, so that would be 14.5% would have to be for the butadiene, HTT, whatever it is called right here, this. And that would be 80.6% of 18%, gives you 14.5%. So we have 14.5% times the density of HTPB. And that density you find online. And then you add like whatever percent you choose in here times the density of aluminum perchlorate, which you find that value online. And you have all these components' densities multiplied by their weights, and you get the total density. And so with those constraints I just talked about, we want to make sure that the percentages that we choose within these ranges, if you choose this or this one, they all create this formulation that gives you the final correct density. Yes, so to talk about the metal additive, if we go here into this spec sheet that was given, it talks a lot about zinc. And I don't know exactly where they state it, but zinc is the metal additive. It's talked about everywhere. So use zinc for the metal additive. And so you just look up the density of zinc online, use this value. Make sure all your units are consistent. You multiply by the percentage that you choose that makes sure that the solids are within 82%. So the solids are zinc, ammonium perchlorate, and aluminum powder. So the percentages of all those components should add up to 82%. So likely you're not going to be getting the exact ratios of the components correct the first time you calculate. You're going to have to check what value of density, total density you get, and compare it against this value, and then recalculate with a different breakdown of percentages. And for part B, we need to use CEA run. Part B is to use CEA online to calculate the specific impulse and characteristic velocity performance. And they give you a range of chamber pressures from 1 MPa to 10 MPa, and assuming nozzle expansion of 0.101 MPa ATM, or atmospheric pressures. So this is the same problem, except now we're going to find a more exact solution. So we have a rocket, and so for the low value of chamber pressure, it's 1 MPa, but we want to put this in ATM. For the high pressure, it's 10 MPa. So put that number in, and then do an interval of 10. I think it's an interval of 10. And then, so for the fuel, we have those components minus the oxidizer, which was this component. So in order to add multiple fuels, we need to go to use periodic table, accept the fuel, and then for butadiene it's H and C, I think. Yeah, and then you select butadiene right here. Then you want to select another one. Okay, then we have zinc is a component of the fuel. Okay, so it's going to be a little loud from now on, but I had to move spots. So we're going to have zinc as part of our fuel as well. So Zn. Okay, so we've got zinc. Then it's going to ask you to choose one of these. You can choose any one. I'm just going to choose this one. And now we need the aluminum powder. So I'm just going to do aluminum. And again, any one is fine. Actually, this is a solid. So don't do the liquid one. because we need 82% solid, so that's important. So now we have all our fuels. Now we need to adjust the mixture percentage. So that's going to be the percent that you roughly discovered with your estimate from part A. So just put the percentage in there, then click this. And then for the properties, all you have to do is put the temperature for room temperature in Kelvin. And I don't know why it's room temperature, but it is instead of sea level. And that value is going to be 293 degrees Kelvin. Don't put the densities in that you found from online because CEA is smart enough to figure that out based on the temperature and more information. So that's why we want to use CEA, because it's more accurate. So then we want to do the oxidizer. And so the oxidizer was the aluminum perchloride. And we're going to need to look up that chemical online to see what its chemical makeup is. So we can put the elements in correctly. So NHClO. So we need NHClNO to be selected from the periodic table. So right there we have helium, Cl, oxygen, and N. There we go. Then just pick either one, I think. Then accept, and then you just change that to be the percent that you found with your part A. And again, room temperature here. Then the next tab. So this is going to be the percent of oxidizer to fuel. So you're going to get a percentage for the oxidizer that's within either one of these ranges. And then you're going to do 100 minus that number is going to be the percent of the fuel. So that's the percent that you want to put in there. And just put that right here. And instead of this, just click this, put it right here. Then click accept. Exit conditions. So they give you PC, the minimum and the maximum, and you're only going to go up to 10. And because it's 1 MPa is the minimum, 10 MPa. And then you want to make the assumption that it's perfectly expanded. So we're at sea level, so the atmospheric pressure is going to be 1 atm, so is the pressure at the exit. So it's just going to be, you want to make sure that your units are consistent, so instead of MPa over atm, you need to convert that, and then do the intermediate values from 1 to 10 MPa over 1 atm. And then you accept and don't include that. And then for final, you want to make sure that you're in equilibrium, or if you want to do frozen, that's okay. Just make sure you specify that in your assumptions, but I would do equilibrium. Then you press submit, and you're going to get all your values like ISP and your characteristic velocity.